Up to this point, we have only been working with numerical data in R, that is, doing operations that receive and return numbers. But that is not the only kind of data that R recognizes. R recognizes other types of data as well, and these different types of data are what we're going to be talking about here today. So the first data type we're going to be talking about is textual information. How do we represent normal written text in R? These data are called character strings, or even just strings for short. That's computer speak for text. And the way we represent such text is simply enclosing them in quotes, as you can see. So for example, William Shakespeare in quotes would refer to a character string that has the text, written text, William Shakespeare inside it. Textual information, that is in between these quotes, can be assigned to variables just like numbers can be. So for example, I could define a variable called S1, that is William, and then another variable called S2, which is Shakespeare. And from then on, I can work with these variables. For example, if I ask for their values, they will dutifully return William and respectively Shakespeare. There are various operations one can do on strings, and I'm not going to go into the details right now. I'm just going to give you one simple example, and that is the example of merging strings. In computer speak, this is often referred to as string concatenation. That's not very important for you to know. Just if you come across that term, then you'll know what they're talking about. Namely, simply merging two strings into one string by joining them together. And there is one function in R that is called paste, which does exactly that. So paste is an interesting function. It's the first function we're looking at that instead of taking in numbers as input, it takes in character strings as input. Moreover, it will also return another character string as an output. In this particular case, if we input two different strings to the function paste, then the output will be simply those strings put together. And as you can see, if we merge S1 and S2 with the paste function, and S1 is William and S2 is set to Shakespeare, then their merged version will return William Shakespeare. You might notice, if you have acute eyes, that there is something strange that happened here. Namely, William and Shakespeare, if we write them right next to each other, we merge them, should not have a space in between them. That is right. The thing is, the paste function by default will put an extra little space character in between the joined strings. If we do not like that behavior, it can be easily overwritten, because the way it is controlled is that paste has an extra argument called sep, which is by default set to be one single space. But if we set that to the empty string, and the way we represent an empty string, as you can see at the bottom of the slide, is by just writing down two quotation marks next to one another, not writing anything in there. So that stands for the empty string, no text whatsoever. And if we set the separator to that value, then the two strings are literally just put next to one another, and we get the result, which is William Shakespeare without a space in between those names. Now, it is important to be cognizant of the difference between character strings and numerical values, even if they might sometimes look superficially similar. As an example, here on this slide we're defining two variables, a and b, and a is set to be equal to 6.7, a number, a good old number like any other numerical values we've been working with so far. But b is set to a character string, which consists of the characters 6 and the period and the number 7. But because we used the quotation marks, the variable b is not interpreted as a number at all. It is interpreted as a sequence of characters. And that is an important difference. For example, it is a legal operation to multiply a by 2. 2 times a is 13.4 because a is equal to the number 6.7, and 2 times 6.7 is 13.4. Whereas it is not legal to multiply b by 2 because b is a character string. So if I try to type out 2 times b, then I get back an error which says that we're trying to provide a non-numerical value into a computation that essentially requires numbers, like the multiplication that we have here. Okay, so this was sort of a quick introduction into the concept of character strings, textual data that we might represent as such in R. The next data type we are going to be discussing are logical values. So as an experiment, you can try to enter in RStudio, in the R console, the following expression, 2.1, and then the angle bracket, which stands for less than, and then the number 5.3. And if you do this and press enter, then you'll get back the result true. Okay, so somehow these logical operations are apparently built into R. Somehow R knows that 2.1 is less than 5.3. Similarly, if we enter 2.1 is greater than 5.3, then we get back false. It's not true that 2.1 is greater than 5.3. More generally, variables can also have logical values, and the logical value is either true or false, capitalized, so don't write them with lowercase, don't write them with title case, meaning that the first letter is capital and the other letters are lowercase. They have to be all uppercase letters, and these are some of those built-in reserved words in R that you're not allowed to use for other purposes. So they represent the possible values of logical variables and logical expressions. So some examples follow. You can compare numbers with the usual comparison operators. It's just good to know that apart from the less than and the greater than comparisons, you also have less than or equal to. So for example, 2.1 is indeed less than or equal to 5.3. If you would run this in R, you would get back the result true. In turn, you have greater than or equal to, and when writing greater than or equal to, just remember that you first have to write down the greater than symbol and then the equal sign. If you do it the other way around, it will not work. Just giving you the heads up. So, is 2.1 greater than or equal to 5.3? No, it isn't, because 5.3, as we know, is in fact larger than 2.1. Equality we can test for with writing down two equality symbols. So 2.1 equals 5.3 asks the question whether it is true that 2.1 is equal to 5.3, and no, it isn't, it's false. Now you might be wondering at this point, why are we using the double equal symbol? Why don't we just use a single equality symbol? Well, the reason is that the single equality is used for a different purpose. If you remember from the last lesson on functions, it is used to set the values of different function arguments. So in order not to get confused with that, when we're talking about logical equality, then we use two equal symbols. And really, it has a different kind of role than a single equals symbol, because a single equal symbol sets the value of a function argument, whereas the double equal symbol asks a question. Namely, it asks, "Dear computer, is it true that 2.1 is equal to 5.3, and then the computer will give back the result false in this particular case. There is also the opposite of equals, which is not equals, and that is denoted by an exclamation point followed by an equality symbol. So some of these symbols are a bit strange. They take a little bit of getting used to, but if you practice it, it will become second nature very quickly. So for example, as you can see, 2.1 not equals 5.3 is true because it is indeed true that 2.1 is not equal to 5.3. The equality and not equality operators also work with character strings, by the way, and logical values as well. So for example, the character string cat not equal to the character string dog is true because it is indeed true that those two strings are not the same. They would only be the same if those strings were equivalent character by character. As they are not, the claim that they are not equal happens to be true. And also logical values can of course be compared with one another. So is it true that false is equal to false? Yes, it's true. They are the same. Similarly, true equals true would also return true, but true equals false would return false because it's not true that true is equal to false. So now that we know that we have access to logical values, there are also ways to combine them. And here's a small table summarizing some of the operations we can do on logical values. Namely, there's logical negation or logical not, that is symbolized by the exclamation point. There is logical and, symbolized by the and or ampersand symbol. And there's logical or, which is symbolized by this vertical bar symbol. Let us see how they work on a table. The simplest case is the logical negation. Not true is false and not false is true. That's simply how it works, and you have to put the exclamation mark in front of the value that you want to negate. Logical and works a bit differently because it takes two inputs. Both of them have to be logical, and as you can see in the table in the middle, you only get back true if both of the logical values happen to be true. Otherwise, you get back false. And the or, the logical or symbol, works in the way it also takes in two logical inputs, but it only returns false if both of the inputs are false, otherwise it returns true. So let's just see an example. For example, 1 is less than 2 and 1 is greater than 2. Well, that will evaluate to false. Why will that evaluate to false? Because 1 is less than 2, although that is true, 1 is greater than 2 is not true, and then, well, it cannot be true both at the same time, that 1 is both less than 2 and greater than 2. That's the whole meaning behind the AND operation, so this will evaluate to false. By the way, what this little code snippet is supposed to show you also is that, just like with strings, just like with numbers, logical values can, of course, be assigned to variables. So we can assign the result of this computation of 1 less than 2 and 1 greater than 2 to a logical variable. Let's call that LGL for logical. And then once we have that value, and if we ask for the value of not LGL, then what we would get back is true. Why? Because LGL evaluated to false initially, and then we negated that, so then we get back the result true. Let us now learn about a function that is a very important function which works with logical conditions, and that is the ifelse function. And it is an important function because it can be used to discriminate between cases. It's a case analysis where if some condition is true, something happens, otherwise something else happens. So the outline of the function is in the top, as you can see in the blue box. So the name of the function is ifelse, and it takes 3 inputs. The first input is a logical value. By the way, these are often also called predicates. Predicates are simply expressions which evaluate to either true or false. So if you hear people talking about predicates, that's simply what they mean. An expression that evaluates to either true or false. So that's the first input. The second input is the value that should be returned if the condition was true. And the third input is what should be returned if that condition was false. So that's what the if-else function does. Let's show a very simple little dummy example of how that would work. Let's define a variable called less is more, and it is defined as follows. We use the if-else function, and the condition is 1 greater than 2. So we're asking, dear computer, is it true that 1 is greater than 2? The second argument is what should be returned if that condition happens to be true. In that case, we should return the character string 1 is greater than 2! Exclamation mark. Whereas, if that condition turns out to be false, then let's return the character string no, 2 still exceeds 1. Now, since in this case it happens to be the case that 1 is actually less than 2, the first condition, 1 greater than 2, will evaluate to false, which means that the second input will simply be skipped, the 1 is greater than 2, and instead we're going to go on the third input, which is no, 2 still exceeds 1, and that will be the value that is returned by the if-else function, and therefore that is the value that we are assigning to the variable less is more. So less is more will be set to no, 2 still exceeds 1, and that is in fact what we get if we ask for the value of this variable less is more, as you can see at the bottom of this slide. Let us consider a perhaps more inspiring example of how one might use the ifelse function to help simulate real-world processes. So in particular, let us try to simulate a coin toss. And we're going to do this in the following way. First of all, there is a function that is built into R that is called runif, that is used in the first line. This will generate a number of uniformly distributed random numbers in between 0 and 1. And runif takes in an argument which is set to 1. That argument is the number of values that should be drawn from the interval, and they will be drawn independently. In this case, we only want one single uniformly distributed value between 0 and 1. So with equal chance, that number could be anywhere between 0 and 1. That is what we're generating here. Then we're going to be using if-else to decide whether based on that random number we have tossed heads or tails, and we arbitrarily will say that if the toss is less than 0.5, then we'll consider it heads, otherwise we will consider it tails. And then we'll ask for the value of coin. And then this might be different if you execute it on your computer, because the runif function again generates random values, so their values are not predictable in advance. Depending on what that value turned out to be, if it was by chance less than 0.5, then you got the result heads, otherwise you got the result tails. And the thing is, if you keep rerunning this simple 3-line program that generates the toss with a random number, then based on that toss decides whether the coin's face is heads or tails, and then you print out the result on the screen, then every time you will get a different result. So here is a simple example where I run this program 3 times, and every time we get back some different result. Again, the pattern in which these results come out should be different on your computer and on your running R session, but on average, if you run this many times, the fraction of times you get heads and tails will tend to 50-50%, of course, as they should. So that's it for today. Again, in summary, what we've learned is that there is more to R than simple numerical data. We can also represent textual information through character strings, and logical information, expression that evaluate to either true or false. And we've seen in this short 3-line program that we kept repeating that these can be combined in useful ways. Namely, in this program, we first generated a number that was randomly drawn between 0 and 1. Then we used that number in a logical comparison to check whether it fell below or above 0.5. And depending on the result of that comparison, we either returned the character string heads to represent the toss of heads, or the character strings tails to represent the toss of tails. So that's it for today. Thank you for your attention, and I will see you next time around.